Hello everybody, so what's up? So in this video and a couple of videos in this series itself, we will be dealing with the fundamentals of TensorFlow. And probably you know the TensorFlow is one of the most powerful, the most exhaustive and robust tool that you can have in the world of deep learning, along with PyTorch. So both are just absolutely awesome and absolutely powerful. So without further introduction, let's start with the absolute basics. So what we'll be covering in this video is some of the basic definitions of TensorFlow, some of its operations, and the absolute fundamental building blocks. So let's first import it. And check out the version. So I'm using 260. And so first, absolute basic definition, the what is a tensor. So tensor are multidimensional arrays that are used in TensorFlow. Now, all tensors are immutable, like Python numbers and strings. You can never update the contents of a tensor, only create a new one. And one of the fundamental question you may ask is differences between TensorFlow tensor and Numpy array. And they're both, so tensor is a generalized vector. Thus, every tensor can be represented as a multi-dimensional array of vectors, but not every vector can be represented as tensor. Hence, as Numpy arrays can easily be replaced with TensorFlow's tensor, but the reverse is not true. And another difference between a Numpy array and a tensor is that the tensor are backed by the accelerator memory. So means that tensor can be used on GPUs and even TPUs, which is not the case with Numpy array. So we will use some basic definition. For example, rank of a tensor. Quickly check out a nice blog that I found out. Yes, the rank system and dimension. So rank 0, which is a scalar tensor, a tensor containing a single value and no axis, is 0 dimension. That's rank 0 tensor. Then rank 1 tensor is a tensor containing a list of values in single axis, 1 dimension. Rank 2 tensor are tensor with 2 axis, and rank 3 tensor with 3 axis, which is image over here, and it goes on. Rank 4, rank 5, rank 6. All right, now coming back to our code, let's start with initialization of tensor. We will make use of the tf.constant function. Let's define a variable tensor equal to tf dot. Let's say I assign 5, and oh, I forgot to ignore all my warning. Let's do that, otherwise I will get all these thousands of lines of warning across the notebook. Warnings, and then warnings. Warnings. Here. So it says that it's a tensor with because I have not given any shape, so that means it's a scalar value actually. So that's what it is showing, that it has no shape or shape 0, and its d type is in32, and the value is 5. So let's quickly find out what this constant function is all about. Let's go to their official documentation. Then remember that TensorFlow has one of the most beautiful and very exhaustive documentation in the world of software engineering. So this is the tf.constant documentation, and what it says is creates a constant tensor from tensor-like object. And go a little further, there's a lot of details here. All right, this is a nice information. All eager tf.tensor values are immutable in contrast to tf.variable. There is nothing specially constant about the value returned from tf.constant. This function is not fundamentally different from tf.convert to tensor. The name tf.constant comes from the value being embedded in a const node in tf.graph. Okay, interesting information. And the d type is specified. The resulting tensor value are cast to the requested d type. Okay, so we can cast it actually, and if shape is set, the value is reshaped to match. Scalars are expanded to fill the shape. We will do that in a while, right? The next line of code. Okay, tf.const has no effect if an eager tensor is passed as a value. It even transmits gradients. Okay, these are quite a bit of nice information. Let's go back to our code. All right, normally in TensorFlow, you don't necessarily have to initiate tf.constant quite a bit of time in your regular work, because you would mostly be pulling the data from various data sources, and also sometimes from TensorFlow's own data repository with tf.data, etc. But this is tf.constant is like the most fundamental or initial fundamental way to initialize tensor in the tf world. So it's very, very good to know. A quick note before we move on, which is that in TensorFlow, the difference between constants and variables are that when you declare some constant, its value can't be changed in the future. Also, the initialization should be with a value, not with operation. But nevertheless, when you declare a variable, you can change its value in the future with tf.assign function. And the initialization can be achieved also with the value or operation. So that was one of the fundamental difference between constant and variable. So let's move on. We will initialize some other form of constant. Let's do yes. We'll initialize this time with a vector with more than one element, 1, 2, 3, and I will print it. Okay, so now I'm getting a shape of 3. That's only first element of the tuple. There is no second element because it's a one-dimensional array, and the data type and other things are just the same. Now let's do some variation of this. What if I do so equal to, let's, for the sake of time, copy it and add another vector, 2, 3, whatever, 9. Okay, so I have added 2 vectors. Let's see what happens if I print it. And I get a type error, cannot convert 239 to a TensorFlow D type. And probably you have already understood that this thing that is there, it's a tuple, and this is not a tensor. So I have to initialize a tensor. So I have to make it a tensor by enclosing it within these square brackets. And now let's see. And now indeed it's all right. Now it's tensor indeed, and I am getting a shape of 2, 3. So it's a there's 2 by 3 tensor. So I have 2 rows and 3 features. You can imagine in that way. And now let's check out their some of the properties. Let's check out their rank. Print tf.rank. If I do that, let's see what happens. I'm not getting any particular value. It's just showing that rank is a function. So actually the way to handle this is I have to make it a Numpy array. So we make use of an A1B1 array. What was that? Attribute function object has no attribute.numpy. All right, that's because I have not passing anything here. Okay. So the rank is 2. So if you understood that if I do not pass numpy, so let's say I delete that and I do this, then it just prints the same thing that it was printing, that it's a tensor of shape this and retype this, but it's not giving me the rank. To give the rank, I have to use a numpy function to transform the tf.tensor to a numpy, and only then it will give me rank. And in this case the rank is 2 because I have two vectors inside the tensor. All right, so and another way you can check the dimension of a tensor is with the ndim function. So let's check what that is. Range tensor.ndim. All right, so it said two dimension as we expected, 1 2 3 and 1 2 3. There are two vectors here inside this tensor. All right, now let's do a tensor of higher dimension so that we can check out the full visualization of them and how they represent. Tensor equal to tf. So I'm initializing again with constant, and so I will have 1 2 3, and then say 4 5 6. This is my one tensor, and the next tensor would be from here. All right, I'm just going to paste it the whole tensor that I have somewhere else already for the sake of time. Otherwise, it will be a lot of typing here. Okay. All right, so check out the form and the structure of this tensor. I have one vector here, one vector here. So the first one within the array bracket, I have two vectors, same here and same here, and the whole tensor that is within the ending square brackets, I have all these three inside. That is the second level of nested brackets. So let's check out how they show tensor. Yep, they are showing shape as 3 2 3. So let's check out how that conforms to our tensor actually. So these first three is because they have 1 2 3, and the 2 is because each of them 1 2 1 2 1 2, and the last three, that is the last dimension here, is for this, that is each of these vector has 1 2 3 1 2 3 1 2 3 1 2 3. So that's how they're the tensor of shape 3 cross 2 cross 3. And my next topic is the data types of a tensor. So by default, TensorFlow creates tensors with either int32 or float32 data types. This is known as 32-bit precision. The higher the number, the more precise the number is, but more space it would take in your machine. So we can actually modify that while creating a tensor. So let's create a tensor with float 16 data type. Float 16. Let's create a two-dimensional element. And 40, 15, have to enclose the whole thing in there. And I want to specify the data type as float 16. Let's see f dot float 16. Yeah. So, yeah. All right. You can see that now it's saying the data type is float 16. Okay, now my next topic is creating tensor with tf dot variable. So till now we initialized our tensors with tf dot constant here, but I can also create tensor with tf dot variable. And the difference between tf dot variable and tf dot constant is tensors created with tf dot constants are immutable. That is, can't be changed, can only be used to create a new tensor, whereas tensors created with tf dot variable are mutable and can be changed with a function called assign function, which we'll see in a moment. So let's create two tensors, and one with a tf dot variable and another with tf dot constant again, and so that we can check out the difference properly. Tensor. Let's create tf dot variable for fun, and our original immutable tensor immutable tensor equal to tf dot constant 0.6. And okay, and now let's see first how the mutable tensor looks like. So run this time. Okay, you can see that it's already mentioning that it's of a tensor of type variable. D type by default it has taken in 32, and it's an Numpy array form, etc, etc. Okay, now let's try to, so our mutable tensor, the first element is 4 and the second element is 5, that is 0 index is 4. Let's try to change this 4 to something else. So let's say mutable tensor 0, that is a 0th index. I want to assign it to say a number 12. Let's run it, and I get a error, type error, resource variable object does not support item assignment. So what this means is that we cannot change a tensor value directly like this. We have to use a function called assign. So let's comment this out and clear the output. Okay, so what we have to do is mutable tensor 0 dot assign, and assign function's argument would be the value that I want, and now print mutable tensor. Okay, run the cell, and you can see that it has changed. Now the first value is 12 and the second value remains as it was 5. So we saw that with assign we can change mutable tensor, that is, which was created with tf dot variable. Our next job is to create some random tensors with TensorFlow. And what exactly are these tensors? They are random tensors, are tensors of some arbitrary size which contain random numbers. And why we need them is because most of the deep learning process will start by creating some random weights, and that's when we need these functions to create tensors with randomly generated values, and the deep learning process during its run of algorithm through back propagations or forward propagations will fine tune those weights in turn. So okay, so let's check out the documentation of TensorFlow, what they say. So there are mainly 3 functions. As you can see at the top, generator function, normal, tf.random.normal, and tf.random.uniform. So how they work is that tf.random.generator will create a generator for the generator first, and from that generator we can create random or normal. So let's start the process and quickly see how the output turns out to be. Random gen equal to that would be a can seed. Okay, a quick note on what these seed is. The term seed is an abbreviation of the standard term random seed. TensorFlow operations that produce random results accept an optional seed parameter, what we see here. If you pass the same number to two instances of the same operator, they will produce the same sequence of results. If you don't pass a number to such an operator, it will produce different results on each execution. So basically, if we want reproducibility, that is, if we want two variables created similarly with a similar kind of random generator to have the same tensors, then we have to pass this seed. So this is not a TensorFlow specific term. In fact, almost any programming language have a seed for random generator. With a seed, you make sure that you can reproduce your results when using random generator. Using the same seed two times would result the same random number. As simple as that. Okay, let's proceed. Random. First, I want to create a random, normally distributed. So let's check out what's the documentation on tf.random.normal. So it says it outputs random values from a normal distribution. It takes a shape, and the default values for this argument, mean, stddev, standard dev, is 0 and 1 respectively, which is what you want for a normal distribution, normally distributed number. It may take a set seed parameter. All right, first just create one simple one with this just a single argument, which is shape. Actually, I don't need, sorry about that. I want to use a random gen variable here. Dot normal. Take equal to let's do 2, 3, and print it. TensorFlow has no attribute generator. Where did I miss? TF, yes, I missed the random. Okay. All right, it worked fine, and it created a tensor with normally distributed values as the individual element, and it is 2 by 3 tensor. We can see that it has got 2 rows and 3 columns, so to say. Okay, now create one for uniform distribution. Random uniform. Check out the documentation again. Yes, outputs random values from a uniform distribution, takes a shape as argument, and all the other arguments look similar. The generated values follow a uniform distribution in the range of min value, max value. The lower bound min value is included in the range, while the upper bound max value is excluded. It's typical Python kind of practice here. For floats, the default range is 0, 1. In the integer case, okay, all looks beautiful. Let's do. I'm going to use the same random gen variable again, which is my generator dot uniform and shape equal to 2, 3 random uniform. Yep, Very well. It created tensor, and this is supposed to be a uniformly distributed tensor. Okay. Okay. Now let's understand the seed concept a little bit better, because you'll be using it in quite often in many places, and some of the nitty-gritties can sometimes create some hard to find bugs. So let's see two lines of code and see if it makes sense. I'm declaring a variable with shuffling few numbers and seeding it as well, and creating a numpy array. Tf dot shuffle, and let's say I'm giving it 1, 2, 3, 4 on a farm, and seeding it to, let's say, 2, 3, 4, 5 dot. Oh, sorry. Here goes my numpy. Okay, let's check out what it prints. Yeah. And now I'll be creating another variable with the same line of code, and now let's print both print A, B. So these two lines, I'm creating same lines exactly. A and B variable, they are both creating random shuffling of numbers, and the seed is also exactly the same, 2, 3, 4, 5. Now it should be the same. That is, A and B should bring me the same numbers always, but let's see what happens. Okay, we can see they are not really the same. 5, 1, 2, 3, 4, 2, 4, 3, 1, etc. So yeah, a better way to check if they are same is I can just do equal to, and now they will be checking each element between A and B, and if they are not same, they will produce false, and if they are same, they will return me true. So I can see that they are not same because I'm getting false, true, false, true, false. And this is confusing because they're exactly the same lines of code, and seed is the same, but how that is different? And the explanation is because there are two seeds concept in TensorFlow. One is a global seed and another one is operational level seed. Let's check out the documentation, what they say. Okay, so I'm in this set seed API of TensorFlow, and it very clearly says that operations that rely on a random seed actually derive it from two seeds, the global and operational level seeds. So its interactions with operational level seeds is as follows. There are 4 points. You have to understand these 4 points very clearly, because that's where we will be making mistake if we don't understand it very well. So number one is, if neither the global seed nor the operational seed is set, a randomly picked seed is used for the op. If the global seed is set but the operational seed is not, the system deterministically picks an operational seed in conjunction with the global seed. And number three, if operational seed is set but the global seed is not set, a default global seed and the specified operational seed are used to determine the random sequence. And the last one is, if both global and operational seed are set, both seeds are used in conjunction to determine the random sequence. Okay, so now what we have to do to get A and B exactly correct, we have to declare the global seed, and which we do with set seed function. So let's do it in next cell. So I'm sorry, I'm declaring the global seed at the top of the lines, df random dot set seed. And what was that? 2, 3, 4, 5. And now I'm just copy paste, and now I'm declaring the variable A. And then again, I am declaring the global seed here, and I am declaring the second variable. And now check if they are true or not. A, B. Okay, let's run it. And now I see that I'm getting true, 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 and true. So the important point is that the call to the global seed with tf.random.setSeed should be done before each operation. So I found a very nice Stack Overflow answer here. It explains very well that the question was global seed and operation seed in TensorFlow 2, how they are different. Uh, and the answer, it says that in short, tf.random.setSeed or tf.setRandomSeed will guarantee that all operations will produce repeatable results across session. It will set the operation seed deterministically for every operation. And but setting operation seed makes sense only as part of operation definition. tf.random.uniform and 1 and the seed 1, and will also lead to same sequence produced by the op across session. So what's the difference? So main point is operation seed makes single operation deterministic. You can create two ops that will produce same operation sequences. Sorry, but graph seed makes all ops repeatedly deterministic. Use it if you want to fix all ops. Different ops will still produce different sequences, but repeated across sessions. Now let's talk about this very important TensorFlow topic, which is tf.data API. Uh, this concept revolves around the concept of a data set which represents a sequence of data items. Let's quickly check out the official documentation. What does it say? Yeah, so the tf.data API enables you to build complex input pipelines from simple reusable pieces. For example, the pipeline for an image model might aggregate data from files in a distributed file system, apply random perturbations to each image, and merge randomly selected images into a batch for training. The pipeline for the next model might involve extracting symbols from the raw text data, converting them to embedding identifiers with a lookup table, and batching together sequences for different length. So basically, the tf.data API enables creation of flexible and efficient input pipelines by delivering data for the next step of training before the current step has finished. So let's do some basic coding. Of course, we'll deal with this in much more detail when doing actual projects. So let's build our TensorFlow dataset. I'm just defining a variable x to be tf.range one minutes. Okay, so this is a tensor with shape of 5. It's a scalar value, and d type of int32, and sorry, it's a vector. Actually, it has 0 1 2 3 4, that is 5 elements, and d type is int32. Now this is a tensor format, and I will be converting it to a numpy, which I can do with numpy, converting it to numpy because I want to just check the actual numpy array values of them. And this is an numpy array value 0 1 2 3 4. Okay, now let's convert the dataset to a TensorFlow dataset with the function called from tensor slices. Data set equal to tf.data. Notice that I'm using tf.data API here. Dot data set dot from. Do I have on the IntelliSense any of them? From tensor slices, yes. From tensor slices, and the argument is x. Run it. What happened? Uh, some problem in my IDE. Quite another time. Okay. So this data set that we just converted with this function, now it's a TensorFlow data set. And notice the shape it's showing to be a empty braces. So we'll come to that later. So basically from tensor slices function takes a tensor and creates a tf.data.dataset whose elements are all the slices of x along the first dimension. So dataset contains here, this dataset, this variable contains 5 items, namely tensor 0 to 4. Now we can actually read them, we can actually print or iterate over them, the data. So let's do that. Item in dataset. Print item. Again, some problem with my IDE. Yes, and they're printing, they're iterating over the individual values, are printing them. So further on the same topic of datasets, depending on the data position and format, the tf.data.dataset class offers quite a few static methods to use to create a dataset easily. And some of them are when tensors in memory, I have tf.data.dataset.from tensors or from tensor slices, which we saw earlier. In this case, the tensors can be numpy arrays or tf.tensor objects. Also, I have from Python generator function, that is tf.data.dataset from generator. And the other one is from a list of files that matches a pattern, that is in that case tf.data.dataset.list files. And there are two specialization of tf.data.dataset object created for working with two commonly used file formats, which are tf records and text line dataset. TF records, we will come to it a little later. It's for now, the main key point about this is it's a hugely useful one when dealing with large data, because when I convert normal NumPy array or some other forms of data to TF record format, uh, the processing and dealing with them becomes much more optimized and much more efficient. And now I'll do a quick example to see some of the basic applications of this dataset class. Let's say we want to define a dataset that produce an unlimited number of vectors, each one with 100 elements of random values. This is exactly what I will do in a future video on generative adversarial networks, that is a GAN project, because this is how I initialize many variables while doing deep learning projects. So using so here I'll be using tf.data.datasets from generator function. Let's start the coding. I'm defining a function noise to generate some random uniform variables. Yield, yeah, random dot. I'm generating 100 of, sorry, it takes a couple 100 of them. 0. Okay. Data set equal to, yeah, data set from generator. Noise, and I have to pass second argument, which is the data type f dot load 32. Oops, I went to the home screen. All right. And only peculiarity of this from generator function method is that the need to pass the type of the parameter, that is whether it's tf.float32, float16, etc. As a second parameter. This is required since to build a graph, we need to know the type of the parameter in advance. And now I will be using the next very important thing about dataset, which is method chaining. So using method chaining, it is possible to create new dataset objects, transforming the one just built to get the data our machine learning model expect as inputs. For example, if I want to sum 10 to every component of the noise vector, shuffle the dataset content, and create batches of 32 vectors each. All these three things I can do by chaining three methods together. Let's see how to do. First, I'm declaring a buffer size and batch size. So buffer size, because I want to sum 10 to the components of this dataset. Oh, did we run this cell? Check out the output. Dataset. Okay, so dataset tf.data from dataset generator. Okay, let's see what happens in the when I make use of this dataset variable later in this cell. Dataset, buffer size, and batch size. Batch size is equal to 32. I want to do this execution in batches of 32. Dataset equal to that. Lambda x plus 10. And I want to now this is the magic of chaining. I want to shuffle this buffer size, and I also want to batch this. Batch size. My normal code intelligence is sometime getting confused with tab9, which is a new extension I just installed here. Batch size. Okay. Too much of code intelligence now coming on my way. IDX. I want to enumerate through this dataset that I just created after chaining. Dataset IDX 2. Correct. Print. I just want to see the output from this dataset by enumerating through this. Oh, not this. Okay. The shape of the noise. Now, let's run this. And as expected, I got 3200 and 0. Okay. Yep. So that was a quick show of this map function and the chaining technique. So the map method is the one that I've used here. It's the most widely used method of the dataset class of TensorFlow, since it allows us to apply a function to every element of the input dataset, producing a new transform dataset. And the next one, shuffle. This method is used in every training pipeline, since this transformation randomly shuffles the input dataset using a fixed size buffer. This means that the shuffled data first fetches the buffer size element from its input, then shuffles them and produces the output. And finally, the batch method. This method gathers a batch size elements from its input and creates a batch as output. The only constraint of this transformation is that all elements of the batch must have the same shape. So be careful about the shape. All right. Thank you for watching this part one of this series.